chemistry, we are surrounded by synthetic materials and molecules more than ever. And our modern society, we are dependent on these materials in such an extent that without it, our modern system is not sustainable. Here in my talk, I'm going to talk about how to make these materials and molecules in eco-friendly way and how enzyme can guide us to achieve this enormous task. So let me first start with an example, very easy. If you wake up in the morning, what we do, we brush our teeth. Now the brush and the teeth both are synthetic materials. Next thing, maybe a cup of coffee. The caffeine organic molecule inside coffee, a natural stimulant, necessary for many of us. Fuel in the gas stations to necessary medicines to survive. All are product of chemistry. Now, have you ever wondered how these molecules have been made in the lab? Let me tell you a story. It's quite similar to building a house. Now, for making a house, you usually start with the ground and then make the pillars and then the corners and finally the ceiling, and your house is ready. So making the corners and making the ceilings might come with different knowledge and expertise. Similarly, when we chemists start developing a target molecule, we usually start with relatively small molecules. For this case, compound 6 and 8 started to make vitamin B12, which is really big molecule. And then we stitch those molecules in a way that we can furnish our target vitamin B12. And we keep on stitching those molecules in a proper way. Of course, it needs a lot of expertise and depth knowledge and where to connect, how to connect. But this is usually it is done. Most of the organic molecules, they exist as mirror images, which means they are similar, but they are mirror images to each other. Just like our pair of hands. They are quite similar, but they are not superimposable. But they can be distinguished by a symmetry element, which is plane of symmetry. And this pair of molecules we call enantiomer. Now, why this enantiomer are so important? Let me tell you an example, infamous example of thalidomide. So thalidomide is this molecule, usually exists as two enantiomer, R enantiomer and S enantiomer. Now, in those who are not from chemistry, the chemistry representations for an enantiomer goes, as you can see, carbon and nitrogen bond. The black bond showing it is above the plane because the molecule is 3D and we are showing in 2D fashion. And the S enantiomer, look at the CN bond, is it dotted, which means below the plane. That's how we distinguish that these are enantiomer to each other. Now let's go back to the example. So this molecule was developed in 1950s by a German company for the treatment of morning sickness, cold, flu for pregnant women. And it was later found out that the R enantiomer has only the beneficial properties and the opposite enantiomer, which is S enantiomer, was toxic. And because of this, more than 10,000 babies were born in between 1950s to 60s with severe birth defects, and many of them died like in a few years. So this highlights the point why you have to make only one enantiomer. Now, in our bodies and our other biological systems, enzyme catalyze reactions. And these reactions are very specific, meaning it only make one enantiomer. And enzymes are really good at it because it has been evolved for millions of years for a specific task. For example, alpha-keto acid in our body was transformed to alpha-amino acids, which is very important molecule for our survival, in presence of amino acid dehydrogenase. And showing this carbon nitrogen NH2 deep bond, showing that it's only one enantiomer. Now, making enantiomer in the lab is a difficult process, and enzymes are not always useful to do it. To make enantiomer in the lab, we need catalysts, and traditionally these catalysts are made from this metal element, particularly this block of element. Rhodium, palladium, iridium, platinum. Chemists made different catalysts like this to make different enantiomers. Now the problem using these elements are because these elements exist in very low quantity. For example, iridium let me use the pointer. For example, iridium, this material, abundance around 2 parts per billion. So it's extremely rare, and most of the resources are already used. So that's why if we make any product out of it, it will be very pricey. Next is toxic. So these elements are usually very toxic to human health. So if you make any product out of it, this metal has to be removed after that. So these also create a difficult other challenge. The third one, these catalysts are very unstable in air and moisture. So handling it very difficult. Usually we keep this catalyst inside glove box. So this also a difficult and expensive process. The chemists were thinking about alternative ways for a long time, a sustainable and eco-friendly way. So this comes until 2000, when Benjamin List was a postdoc in USA, and he discovered that for making enantiomer, we don't need enzymes or metal catalysts. Only a single amino acid can do the same transformations and make enantiomer very efficient. So because of his first development and also contributions for almost 2 decades, he was awarded Nobel Prize in this year, 2021. And the field now known as organocatalysis. So catalysis using organic molecules. Now there are various advantages use this kind of small molecule as a catalyst. The first one, found in nature, so resourceful. Second one, that's why it's cheap and safe as well. Third, it's stable in air and moisture. So handling is very easy. So in our lab, we are also working on this field organocatalysis. Before I go into my topic, let me explain for non-chemists what is electrophile and what is nucleophile. So electrophile is a substance or molecule which is electron deficient, and nucleophile is which is electron rich. So it means the electron flows from the rich to the poor, and that's how we got a reactions and the corresponding product. Now in our lab, I am working on this molecule, ethyl pyruvate, and I want to use ethyl pyruvate as a nucleophile to create this kind of product, of course using organocatalysis. Now this kind of reaction is known in the enzymes, but without enzymes it is almost very difficult. It's very difficult to get this kind of product. Now we are interested in making this kind of product because this molecule can be transformed to other various important molecules very easily. For example, alpha amino acid derivatives could be obtained, and this molecule has wide use. Amino acid wide used in commercially as well as in research as well. For example, you can use branch chain amino acid. You can use if you go to the gym as a supplement for muscle up. So in synthetic biology, in medicine, alpha hydroxy acid has wide application in pharmaceuticals as well as most of the facial cream that you use. Alpha-keto acid as food and feed additives and many more. So these are wide applications if you could make this product. Now in this slide, we will look into what are the problems when we want to use pyruvate as a nucleophile. The first point that come across is pyruvate is very weak nucleophile, which means we want to use a property of a molecule which is already lacking. So look us into the structure of ethyl pyruvate. Ethyl pyruvate is 3 carbon centered molecule. This box showing it has 1 nucleophilic reaction site, and other 2, one is keto and ester is electrophilic reaction site, which means it has 2 electrophilic reaction site and 1 nucleophilic reaction site. Because of having 2 electrophilic reaction site, this molecule in generally is electrophilic in nature, which means electron deficient. So that's one of the problems if you want to use as a nucleophile. Suppose we could generate nucleophile like this. The next problem comes of its homoaldol reaction. Because I already mentioned it has an activated electrophilic center, when we generate a nucleophile, it usually reacts itself and it doesn't want to react with others. So that is one of this reaction known as homoaldol reaction in chemistry, and this kind of product is formed, and also it's cyclized to give different other products as well. So in general, homoaldol reaction is very easy to happen for this case, and if you want to have a cross reaction, if you want to use pyruvate to react with other, we have to deal with this. Anyway, From here, our reaction development starts. So for our reactions, we use pyruvate as a nucleophile, this molecule, and other electrophile. We choose this one because corresponding product could be used for other applications as well. We used this catalyst for our first trial reaction, found out this reaction did not occur. And this catalyst, probably you could remember, was first introduced in 2000 by Benjamin Lewis for his Nobel winning work. We found out that our catalyst is reacting with the pyruvate to make this irreversible product, and that's why our catalyst is getting quenched. We hypothesize that maybe because this carboxylic acid in the catalyst is in alpha position, this product is possible. So maybe if we make a distance of carboxylic acid in beta position, it might help to get quenched of this catalyst with our ethyl pyruvate. So we designed different catalysts and synthesized this kind of catalyst in our lab for our trial reaction. Found out that could see the beta position here. So these are a bit different than the L-proline. Found out that this catalyst also was not very effective for our product. So then we look back to the biological system in your body, how pyruvate has been used by pyruvate aldolase as a nucleophile. So it is known that pyruvate aldolase, which is aldol, which promote aldol reactions between pyruvic acids and an aldehyde electrophile and produce corresponding product very efficiently. And here pyruvic acid pyruvate has been used as a nucleophile. From the mechanistic insight, we have also found out that the primary amine group in lysine of this aldolase create an enamine intermediate. This intermediate was the key for this successful transformation. So then we started thinking about maybe in our catalyst having this primary amine group is crucial. So with this hypothesis, we wanted to make our own catalyst. Our catalyst comes from this molecule quinine. It's isolated from bark of the cinchona tree, which is a native tree found in South America. So this is commercially available and very cheap molecule. It's also a drug for malaria. So we want to introduce a primary amine group in this molecule. So in our lab, we modified this molecule to our expected catalyst. Look at the difference. The hydroxyl group is changed to NH2 because of ours. And when we introduce this catalyst in our reaction, that was a eureka moment. We found out that using this catalyst, quinine and with an acid, we can make a catalyst system that could make the corresponding product very high yield, 86%, enhancer selectivity 97:3, which means if you want to make this molecule, 97 will be S. If you want to make 100 of this molecule, 97 will be S and 3 will be R. So the selectivity is almost like an enzyme, but this is not an enzyme, it's a very small molecule. Not only that, we could make different other products with very high efficiency and very high selectivity as well. We could also make the opposite isomer, the R enantiomer, just changing the catalyst using a pseudo isomer of the catalyst itself, and look at the selectivity, 94:6. Amazing. So with that, there are also various substrates was done that I'm not showing here. But one of the applications that I mentioned before, that we could easily make amino acids from it. And that is also very important, not only for commercial applications, but also for biological applications as well. So here is one of the scheme. So two products, 3A and 3K, this compound was transformed to oxime using hydroxylamine hydrochloride and pyridine, successfully with very good yield, 73 to 71%, with very high selectivity. And then finally, after reduction, amino acids. Look at the selectivity, 95:5 and 95:5 in both the cases. So you can use this one for our medicinal purposes or anything related. This is the X-ray crystal structure of the compound 6, showing the absolute configuration S. So we can say that this configuration is S. So from our mechanistic investigations, our hypothesized transition state is this. So how the selectivity is coming, why only S is forming. So we found out that in our the benzoic acid, this acid is coordinating with the tertiary amine group in a way that it's blocking one phase of pyruvate in amine. One phase is blocking one phase, so the electrophile comes from the bottom and making only one product, which is S. So from NMR study, we wanted to know how fast these reaction steps are, which could also reveal the inside of the reaction itself. We found out that the first step of the reaction, which is enamine formation, rate is very high, 0.56 millimolar per minute. And the product formation rate is very, very slow, suggesting that this is a critical rate determining step. In chemistry, we call it the kinetic rate is very slow. This is the rate determining step. This is the crucial step. We also calculated the pyruvate consumption rate, this ethyl pyruvate consumption rate from the reaction, and found out it's very similar to the product formation rate, which means that ethyl pyruvate is directly going to the product and there is no other side reactions happening in the reaction. So meaning there is no homoaldol reaction that I already had talked about, that there is no side reaction. We didn't design our catalyst in a way that could slow down the homoaldol reaction, but we found out that it could do it. So to check that, the homoaldol product, we wanted to find out in NMR if we could see the existence of this product. We found out there is a small existence of this product, very small quantity, and it doesn't increase over time. And usually this compound, the homoaldol product, transform to other cyclic product. We didn't find any trace of these molecules as well. So we are hypothesizing maybe this molecule can form a very small amount, but it is in equilibrium with the transition state, giving back one monomer of ethyl pyruvate again to the reaction so that it could go to the product formation. So this is very critical point, that our catalyst system is not promoting homoaldol reactions, which was always found to be this case, and it only working for our product. So the selectivity is also very important, because this catalyst system can be generalized for other type of bond formation reactions as well. So that's basically it. So if you could remember, in conclusion, we have developed an organocatalytic enantioselective version of managed reactions of pyruvate as a nucleophile, and this is one of the first kind of example non-enzymatic reaction that could be possible. Simple pyruvates like this kind of pyruvates, which was always found very difficult to use as a nucleophile, was used. From mechanistic investigations, we found out that the pK of the acid, not only pK of the acid, but also the structure of the acid was important with the amine catalyst as well. And the last one, our catalyst system that we developed, it's worked for our desired managed reactions, managed product, the product we got over the self-aldol reaction. So which we could generalize these reactions to other type of reactions as well. So we are currently in a position that we could use this catalyst system, and we are checking it what kind of other bond formation reactions possibly you could do. That's it. Thank you very much. Any questions? Yeah.
What's the temperature and reaction condition?
It's room temperature.
Oh, okay.
Yeah, it's like like physiological condition.
And how long?
Around most of the cases 20 to 21 hours. So relatively short time for these sort of substrates that I showed. Yeah.
Okay. So you use this beta amino group in the quinine amine. So have you tried the opposite isomer to synthesize the opposite your expected product?
Yeah, exactly. That's what I mean. So quinine amine, it produces the S enantiomer. So this quinidine amine, which is a pseudo isomer, which is an enantiomer of the catalyst itself. So if you use, then it produces the opposite isomer. So you can access like two enantiomers at the same time, and with really good efficiency and selectivity as well.
And you synthesize the opposite enantiomer of your catalyst also?
Yes, these amine molecules are not commercially available, as far I know. But the hydroxyl group, the quinine of its quinine derivative, the OH derivative is available because it's natural resources, because we can easily extract it from there.
So even the best reaction doesn't give 100% selectivity the product enzyme that you want. So I wonder, like, how difficult or how expensive is it to separate the enantiomer you want from a mixture?
A very important question. So if you want to use as an enantiomer drug, before you get FDA approved, it has to be almost more than 99%. Right? In my case, you could see it is like 97:3. The thing is, there are options like crystallizations or resolutions. We could improve this 97:3 to more than 99% very easily. But then in that case, we lose some of the compounds as well, because recrystallization is like you solubilize and slowly make it crystal. So the enantiomer, they separate out. But in this process, we also lose some compounds. Some of the compounds will be in the solutions as well. So there are process, but if it's 50-50, like a racemic mixture, then you cannot. In most of the cases, you cannot resolve it. So technically, we can improve it for a specific purpose, but it is not important right now because we don't know the kind of applications that we have.
Are they planning to scale up the production of this?
We already done it like more than, so these reactions are like around 74 milligram scale, but we have done in more than gram scales as well. Usually before we publish the paper, we have to show that this is reproducible and in a large quantity. So we have shown in more than a gram, so it is quite efficient in this ratio. So some of the substrates we have done producing like similar selectivity and also like similar yield.
How about industrial scale?
So we go for, I think it is possible, but I cannot guarantee, because then probably because industrial scale and the lab things go a bit differently, because their equipment handling, like if you want to make a product in a ton scale, so you need a bit different optimization. Maybe we need to use probably if you see the catalyst condition, 10 mole % of the catalyst was used. Maybe you have to use a bit more to make even tons of like product for industrial purposes. But it is possible technically. We just need to re-optimize a bit.
And is this reaction also enzyme catalyzed? No.
Particularly these reactions is not known, but this type of reaction is known. Like I showed one aldol reaction, or other conjugate reactions are known, but this is not known. So it's in a way, it's like artificial reaction, but it's kind of inspired from kind of enzyme. I think the organocatalysis, the field itself, inspired by how the enzyme works.
Another question?
Okay. So you were inspired on like natural like enzymes, right?
Yeah.
And the active side of the aldolase is like lysine. Why did you try lysine, or like a 3 or 2 amino acids, amino acids? Is that one?
So again, I'm not very clear.
You try like lysine or like the amino acid with lysine?
Well, we did not use these purposes because before we get to that point, we already got a really good metrology. But there are reports where, like not L-proline, but lysines and other amino acids was used to catalyze, not this one, but there are different ketone molecules are in organic chemistry. Just simple ketone was used to catalyze reactions, and it was found in some cases that you could make a corresponding product with very high selectivity. But in this case, we didn't. If your question is, in this case, we didn't do it because lysine, because not only, so in enzymes, lysines is important, but also the whole structure is important for the selectivity. So lysine might, like having a lysine residue might promote the product, but because you want to make only one enantiomer, so selectivity is also as important as the product formation.
Lysine derivatives.
We did not, because we did not, because just but we could try.
About these questions, let's make again Santalu.